Hi there, and welcome to this Integrated Math 2 video series. This is Unit 2, Video 4 in this series. Today we're going to talk about quadratic regression and how to model real-life situations with quadratics. And before we get into that, let's go ahead and start with our warm-up for today. We've got 5 problems here for you. Take a minute and try and do these. Okay, so in number 1 here it says create a quadratic function with x-intercepts of 3, 0, and 2, 0. Again, those are the points where they cross the x-axis. In our last video, we talked about 3 forms of quadratics. We talked about standard, factored, and vertex form. One of the ways we can connect characteristics with a quadratic like this is using factored form, because we have the x-intercepts, or the zeros of the function. So the zeros are 3 and negative 2. The x-intercepts are 3, 0, and negative 2, 0. So what we can do is we can set up factored form with x minus 3. That would make 3 being the 0 of this factor here. So meaning that the x-intercept is that. And then x plus 2. So going backwards now, given some characteristics, coming up with the form. Again, thinking about what characteristics match up well with what form is really important. Now, this is one version of a quadratic that has these x-intercepts, but there's actually an infinite number of quadratics that have these x-intercepts, because we can put any sort of coefficient out in front. Right now, it's just a coefficient of 1 that's assumed there, but we can make it whatever we want. We can make it even a negative number, maybe a negative 4, so now it's concave down, it's opening downward, but still has those x-intercepts. So you can fill in that spot with whatever you want and still satisfy the situation. All right, number 2. Looking at some mental math here. Let's see if we can multiply these 4 numbers together with ease here. So you could try and multiply, from left to right, or you can think about it this way. 2 times 5, you may have seen that before in a previous video. 2 times 5 is 10, and then 3 times 4, that's 12. So really it's down to 10 times 12, which is 120. Number 3, describe how you would increase 452 by 6%. So there are multiple ways to do this, but the easiest way, with the fewest operations, is to multiply 452 times 1.06. So that's 106%, so an increase of 6% of 452. And so you can figure out that new value there. What is the vertex of this function here? So this is, remember from previous video, vertex form. So we can tell the vertex rather easily here. So this 2 does not impact the vertex at all. All that 2 does is change the vertical stretch or compression of the function. We'll talk about that in our next video. But here, let's see. It's going to be whatever makes this 0. So what makes this parentheses here 0? X being negative 5 would make that 0. So negative 5, comma. And then if we think about if this is 0, by plugging in negative 5 here, 0 squared is still 0, times 2 is still 0, minus 1. So when we put in negative 5, we get out negative 1, and that is the vertex of that function. So in general, you can think about it this way. It's whatever x value makes the parentheses 0, and then this number out here, we called k, is always going to be the y value of the vertex, if it's in vertex form. All right, lastly, number 5 here. What function type would best represent the relationship described by these points? If you remember back from Integrated Math 1, you looked at linear functions quite a bit. You also looked at describing data with a linear function. So yes, this looks kind of like it's in a straight line here, roughly, and a linear function would be the best function type to fit this. So if we were to draw the line of best fit, is what we would call that. It would be, something, around there. Would be the line that best fits that data. We're going to talk more about this today and expand upon the options that we have, because back in integrated 1, really the only option you had was a linear function. You didn't have any other types of functions to use to describe that data. So that is just our goal for today. That's it, is use other function types. So in this case, a quadratic function, because that's what this unit is on, but really you can use any function type. We're going to talk specifically about quadratic functions today and how to model real-world relationships. And that's the whole point of this, is to make decisions based on data, but using functions. And so let's kind of get into that right now. So if you look at this data now on the screen, hopefully you can see that. If you were to try to draw a line of best fit, so a linear function, it would be very difficult to do. And even if you did, or were able to do that, it would not describe that relationship very well. The relationship between x and y that we're seeing here would not be described very well with a straight line. But if you remember what a quadratic looks like, a quadratic would fit this data actually pretty well, right? And you can think about maybe what that would look like if we were to draw a quadratic. Rough version of that would look, something like that. So that's our goal for today, is be able to use technology to figure out what would this function actually be. What would this quadratic in function form actually be? So, and how would we use that function to find out more about the situation than we already know? All right, so let's hop into Desmos. This is Desmos. You can get to Desmos just by going to desmos.com. That's DESMOS.com, and click on the graphing calculator. And this is the piece of technology that we're going to use today. I'm going to show you how to use your TI-84 calculator here in a bit, but we're going to start with Desmos. So click on the graphing calculator, and then you can have access to something like this. So I'm going to show you how to type all this in just a minute. Well, actually, I'll kind of show you the basics right now. So what you would do to get this table here is you could just hit plus and then hit the table button, and that'll create a table. And you can start typing in these numbers here if you'd like. And then this table is going to automatically be shown over here in these points. So you can see the table showing up in these points. So for example, 4, 6 would be 4, 6. It's that point right there that's plotted there from the table. And so what I wanted to show you with this first part is just that, like, we can use Desmos to come up with a line of best fit. Again, something you do back in integrated math 1. So we can do that with this right here. So you can do y sub 1, so just type in the letter y followed by the number 1, and it'll automatically become a subscript here. And then this like tilde looking thing is at the top left of your keyboard. You have to hit shift and then press the button at the top left of your keyboard to get that symbol there. Because we're saying it's an approximate relationship here. This linear function is not a perfect fit to the data. So that's what that tilde means. Like it's an approximate, it's a best fit here. And then you can represent your unknowns with anything. But typically m, x plus b is the form. So type in m, and then x followed by the number 1. Because again, that's what we call these up here. So this is x1, y1. You could have another table with x2 and y2 or something like that. But anyways, we're talking about these two columns here, and then plus b. And that should create this line here. You won't have the function that shows up. I did that with a special a way of doing that. But I just wanted to see what happens when we move these points. So I'm going to move these points, and the way I did that was I held down this button right here, and it'll ask you if you want to be able to move the points or not, or drag the points. So I said yes. So that way I can move these points, And you can see how the line of best fit like automatically updates dynamically, you know, as I move this point around. And so you can see, like, if I move it way down here, okay, so now this is the function. So this is a slope of 1.625, and then x minus, and then there's my y-intercept, negative 1.8 is about where that y-intercept is. So it's kind of cool just to see how, like, as I change these points here, like how each one, you know, alters the line of best fit. And as I spread these points out, the line of best fit becomes less and less accurate in terms of representing these points. So I want to point your attention over here to some of the numbers down here. So don't worry about residuals right now. That might be something you look at later if you take a stats course. Right now I want you to look at r squared. So r squared, this number here, it ranges from 0 to 1. 1, if this number was exactly 1, it would be a perfect fit, meaning this line went through every single point on my graph. Obviously, this is far away from 1. The closer to 0 means the worse the fit. This is not a very good fit right now because our points are really spread out and the line doesn't accurately represent the relationship between x and y right now. So that's the indication that this is not a great fit for the data as it is right now. R, you talked about correlation coefficient back in Integrated Math 1. That's what that means right here. So this is a very weak correlation between our two variables. I haven't given you any context in this case, but just between the two variables that we're looking at here, x and y. And then below that are your parameters. So notice that it says m equals this and b equals that. So all that's saying is this line that's showing up here, the m value is 0.32 approximately, and b is 2.4. So really all that's saying is this is the function that is being used here to describe that data. That's all that means. So it's just saying use m and b, that's going to create that line of best fit is when m is this and b is that. So that kind of describes this overall setup here with a linear function, again going back to Integrated Math 1. But now let's go ahead and switch it up a little bit and look at maybe a different type of data set. So this is, I've inserted a picture here of the bottom of the Eiffel Tower in Paris, and we're going to try to come up with a line of best fit that best fits this arc right here. So this arch underneath the Eiffel Tower is going to be fit by this function, and as you can see, it kind of creates this quadratic look, and that's what we're going to model this with. So I've got my data. I just typed in some random points here. Up there is just where I inserted the picture. And I've got a quadratic now that's fitting to these points. So I've typed in y1, and then this tilde looking thing, approximately. And then I typed in ax1 squared, so the caret symbol, that up arrow looking roof thing, the caret symbol, and then hit 2 plus b x1 plus c. So instead of having a linear function, now we're going to switch it up and have a quadratic function, because a linear function would not fit this very well, right? The r squared would be very low if we tried to do that with this arch. Okay, so type that in, and then what I'm going to do, I've allowed these points to be moved. So if you hold this down and select drag, being able to drag it, I'm going to move these points on this archway here, and let's see if we can come up with a quadratic that best fits this archway. So I'm going to drag these down, and obviously we're going to need to think about scale here and the scale of this. So right about there, we've got pretty good fit here to the arch. Okay, so what that allows us to do is kind of model that shape with a quadratic, which is kind of cool. Another thing we can do is look at the quadratic itself. So A is approximately negative 1.1, B is approximately 9.26, and C is approximately 7.3. So if you were to create your function here to model this situation, and again, we'd have to think about scale, but it would be y equals, A is approximately negative 1.1, and then of course that's rounded, x squared plus b, which is 9.26x, plus c, which is 7.3 approximately. So this is a great representation of that arch, and this is the function that would describe it. So it doesn't actually like show me the function. I've got to interpret these a, b, and c values as those are the values that I'm going to input into the general standard form of a quadratic. Ax squared plus bx plus c. All right. So that's just kind of an interesting, approach to this whole idea of quadratic regression. All right, let's look at our next example. Okay, so what we have here, I've typed in this data here. This is the distance of a baseball given the angle at which the bat swings and hits it, and the distance that it flew. So you can imagine, like, if my angle is really low, it's not going to go very far, right? But if the angle is really large, then it's going to go way up in the air and it's still not going to travel very far. But there might be a sweet spot that we can find here in terms of the angle that we need to hit the ball in order to be the maximum distance. So we're going to use this data here. If you want, you can go ahead and just pause the video and type those into Desmos. And then we're going to look at a couple different things here. So take a moment and try and type those in. Okay, so from there, I've actually set up two different regressions. One is a linear, and then one is the quadratic. So let's just compare them. So if I turn on, so I've just pressed this button here to turn it off. I'm going to turn it on now, and you can see it's going to graph that linear function. Not a very good fit, right? Let's check the r squared. R squared 0.26, pretty low, which makes sense because it's not a very good fit. All right, let me turn that one off and turn the quadratic on. You can see that the quadratic is a much better fit here. R squared, let's check it, 0.98. 0.98. That is very, very close to 1. And so it's a very good fit. Basically what that 0.98 means is 98% of the variability is accounted for in this model. And so it's a very good fit to this data. A, B, and C are listed there. And so we could create and write our function out if we wanted to. But Desmos is really nice because it allows us to find out other things about this situation. So if you look at the angles, we went from 10 and the large one was 64. What if we wanted to know about maybe an angle of 70 or something like that? What would be the best prediction for the distance of the ball in flight if the angle was 70? Well, what we can do is we can use this function to predict. I'm going to go down here to 70. $143. So 143 would be the distance. I think it's in feet. Well, actually, it's probably yards. 143 yards is how far it would fly at an angle of 70. Since I picked a point that's outside of the data, so the data runs from 10 to 64. Since I picked 70, which is outside of that range, I guess it's the domain since we're talking about x, but outside of those two values, outside of the data itself, we call it extrapolating. So we're extrapolating outside of the data, and it's not going to be as accurate when compared to interpolating. So if I wanted to know maybe what it is at 53, so 259 yards at that point. Actually, I think it is in feet. That makes more sense. But in terms of the large value there, but since we're interpolating, so inside the data, it's going to be a lot more accurate. So if we try to predict values in here, if we go outside of that, maybe 5 or 6 degrees in terms of the angle there, it's not going to be as reliable in terms of the output value there. So that's kind of what we're going to do here is use this function that Desmos or your piece of technology creates to predict other values. So we can try and think about what happens if we interpolate or extrapolate at other values. And so that's the whole point of this. All right, let me show you real quick how to type it into your TI-84 calculator if you'd rather do it that way. All right, so I want to show you how to use your TI-84 calculator to do these same things if you'd like to use it instead. The first thing you want to do is check your mode here. So hit mode here at the top, and then go up is the quickest way to get there, to stat diagnostics. You want to turn that on. So go over to on and hit enter. And you only have to do this one time. What that allows us to do is see the R² value when we do our quadratic regression. Otherwise, you won't be able to see that. Okay, so here's how we type in our data. We're going to go to stat, which is right here. And we're going to hit enter to select edit. And these are the table of values that we're going to input our numbers into. So you can start typing those same data values in. So for example, 10, and then I'll hit enter, 15, enter, and you just go down the X values first, 20, enter, 24, enter, and so on. And then you'll go over, once I finish the X values, you can go over and type in the Y values, so 115, 0.6, and so on. And then you can go from there. So once you get all the data typed in, as I do here, and if you need to rewind and go back and see all the data, you can. Once you get that typed in, I just quit out, so second mode to quit back to the home screen. And then I'm gonna hit stat. And instead of doing edit this time, I'm going to go over to calc and down to, see all the reg, that stands for regression. So you have a lot of different options here. You have linear regression, quadratic regression, cubic, quartic, those kinds of things you'll look at in a future course. But right now we're going to do quadratic regression. So you'll hit that. X list, so we put our X values in L1, didn't we? We put our Y values in L2, so those are good. So just hit the down arrow to go past those. Frequency list, you won't really use those unless your numbers represent how many of something you have. But that's not the case in most situations. So we're going to skip that. Store regression equation is what that next one stands for. We want to store that into Y1 so that we can actually use the function after we've run the regression model. So what you can do is you can hit alpha F4, which is alpha trace, and hit Y1 there. So what that's going to do is it's going to store it into Y1. So let's hit calculate. Again, kind of similar things that we see from Desmos here. You're going to see the A value, the B value, and the C value, and then it's going to tell you the R², which we have the same R², which is 0.98, as we saw on the Desmos. All right, but from now, you can actually hit Y equals, and you notice that it put the function, so there's A, right, negative 0.18 approximately, X squared, minus the B value, which is about 14.5, and then the C value, which is about negative 21.89 or so. So if you go to the graph, you can see part of the graph, but you may want to change your window. So we can change our x min and x max. The x min we can leave at maybe like -10, that's fine. The x max, let's see, the total distance goes up to about, we'll just say 100 will capture most of, the angle is what is that one is, maybe 90 would be the max. The y min, let's see, we start with 0, but like -10 is fine. And then y max, the total distance, I think highest one would be under 300, so we could just do 300 as our max. So now if we hit graph, we can see a really good picture of that. Another way to get to this screen is to do second, actually it's just zoom stat, and it'll use those numbers we put in the table to show us a good graph of this. All right, so we can use that function to do a number of different things. We can trace. So if you hit trace, you can go along this function and again look at various values either inside the data or outside the data, as we've seen before. So that's how you use your TI calculator to do some similar things to what you see in Desmos. All right, I want to show you another real life situation. So in green here, we have a different county in Tennessee and their COVID-19 totals. And as you can see, as time goes on, these are in days here. As time goes on, the number of cases has increased quite significantly. So if you look at the line of best fit here, the linear function is not a very good fit. In fact, it's got an R squared of 0.63. Not awful, but not very good at all. All right, and then the quadratic is a little bit better. It's 0.92, so not a bad fit. Well, let's think about this. We also have to use our reasoning and sense making and make sense of the situation. So, can the COVID-19 numbers continue to go up forever and ever? Obviously not, right? They don't have an infinite number of people in their county, and so it cannot just continue to go up and up, as we know a quadratic does. So in reality, we might be able to interpolate within, around the data, but extrapolating here in the future doesn't make a whole lot of sense with a quadratic. So I just wanted to give you a scenario in which we can use other types of functions. In fact, using Desmos, you can type in any sort of function type here, and it will come up with the best fit for that data. Now, I'm going to show you what this county is using to model the data. I actually want to show you the function. It's kind of complicated, but this is a logistic regression model is what we call it, and it starts out really small, and then it caps out at a particular value, and so we might think that as we get better at mitigating the virus, that it might kind of slowly flatten that curve as people talk about. And so this is just another example, real life situation of using regression. We're going to stick to linear and quadratic and exponential in integrated math 2, but I just want to show you another situation. In fact, we're not going to get to it this video, but an exponential would be a very good fit, at least right in here, right? Maybe once we go beyond that, it may not be, but it'd be a very good fit within the data that we have right now. All right, in our last scenario, we've got this rocket launching. This is the SpaceX Falcon 9 that launched back in 2016. And I want to show you a graph of this launch and see what we can do with it. So this is the graph here in time. And up here we have altitude, but we also have velocity. So we actually have two things going on in this graph in relation to the time. So you can see the altitude kind of increases, and then it kind of slows down, and then it kind of flattens a little bit, and then goes down in altitude just a hair. But the velocity, you can see it's actually kind of in two pieces. So we have this this part right here, which looks like maybe like a half of a quadratic. And then we have this part here, which also looks kind of like half of a quadratic. And it's in two pieces because this launch involved a two-stage fuel burn. And so you can see two pieces there. Pretty significant difference there between the two pieces. You can pretty clearly see those. So we have some data down here. These points along the velocity curve are in the table here. And I want to see if we can use this data to both interpolate and extrapolate for the situation. So whether you use Desmos or the TI-84 calculator, take a few minutes and see if you can predict using a function of best fit. So you use a quadratic here with this data to predict what might be the best prediction of the velocity at 350 seconds and the best prediction of the velocity at 575 seconds. So take a second and see if you can do that. Okay, so regardless of what method you used, we should be getting very similar numbers here. So I've typed in my data into Desmos. I've typed in my quadratic regression setup here. You can see that the graph is a very good fit to the data, which makes sense because it's a 0.9976 r squared. So very, very good. The A, B, and C are down here. So if I wanted to write my quadratic function, I would write y equals A, which is 0.0011 approximately, x squared, minus 0.37 approximately, x, plus 75.96 or so. So that's a good approximation, at least, of the line of best fit or the quadratic of best fit. Okay, so what we want to do is we're going to look at, I think it was 350 seconds. Yeah, 350 seconds. So I can just go over to 350 my points here. And it looks like 84.783 for 350. And then 575, $236.657. So about 236. So those are some good predictions for those two values. Again, one of them, the one down here, we were interpolating, so it should be a very good estimation. But 575, we were extrapolating. And so you can see that 575 will be right out here. If you notice, it kind of starts to tail off a little bit here. And so our prediction of 575, which was probably way up here, is probably not a great prediction. But if you don't see that tail and you're just using that curve as an estimation, then that estimation was probably a good prediction. So hopefully you were able to kind of figure out how to type these in and then use that function to look at some various situations. All right. So all in all, hopefully we've met our goal for today, which is to use quadratic functions. We've looked at other function types, but at least to use quadratic functions to model real-world relationships. All right, so hopefully you'll join us next time for video 5 in this video series on transforming or using transformations of quadratic functions. So we can kind of actually think about doing this whole setup of finding a quadratic of best fit, but doing it manually, which will be kind of interesting to look at too. All right, so hopefully we'll see you then.